So in this class we'll try to solve some more problems, and this is the continuation of general formalism of quantum mechanics which we have seen earlier. And problem number 1, show that the two operators having common set of eigenfunctions commute. So in this problem, two operators are given, A and B, and they have common eigenfunctions, and we are going to find out these two operators, they will commute or not. So we are going to consider two operators A and B, and A operates on psi I will give us the eigenvalue AI, small ai, and psi I, and of course psi I, right hand side, left hand side we have same psi I, so it's eigen wave function. And B operator operates on psi I will give us small bi, eigenvalue is bi and psi I. So these two operators, they have the common eigenfunction psi I, and we are going to find out A and B operators, they commute or not. Now just take the second equation, B psi I equals small bi psi I. You multiply on both sides by A. So A B psi I will give us A. B operates on psi I will give us bi psi I. So bi is a constant now, so we can pull it out. So I have pulled this side bi, small bi, and A operator operates on psi I will give us ai. So I can write this as ai bi psi I. Okay. Now take the first equation and multiply on both sides by B. So B A psi I, so A operator operates on psi I will give us small ai psi I. So now this equation becomes B ai psi I, and of course A is a constant, it's an eigenvalue, it's a number, maybe a complex number or real number. So now ai, I can pull it out, so ai, B operates on psi I will give us bi psi I. You compare these two equations. Now right hand sides are equal, so if right hand sides are equal, so left hand side must be equal. So left hand side is nothing but a b psi I equals b a psi I. So here a is misprinted, so a will not be there. So b a psi I. So we have just pull right hand side to this side, left hand side we will have ab minus ba psi I, which is equal to 0. So it implies that ab minus ba equals 0 or psi I equals 0. Psi I cannot be equal to 0. Only possibility is ab minus ba must be equal to 0. If psi I equal to 0, that means there is no wave function at all. Wave function exists. So ab minus ba equals 0, it implies that ab equals ba. So ab equals ba, it gives the answer as A commutes with B. Okay. Now we'll go for the problem number 2. Prove the commutation relation, commutation x comma p equals IH class, and we are going to prove both the ways. One is by means of coordinate representation, another one is by means of momentum representation. Of course these two representations are very important. One is just the inverse of another one, in the sense one is just the Fourier transform of another one. So this is what we have already discussed earlier in the classes. So now we'll try to get the answer x comma p equals IH class first by means of coordinate representation, that is by means of x. So xp acts on psi will give us x comma, instead of p we can substitute minus IH class partial d by dx, say operator. So we know the expression for p operator is given as minus IH class partial d by dx. So you just substitute here x comma minus IH class partial d by dx operates on psi. Of course IH class is a constant, I can pull it out. So that will give us IH class x comma minus partial d by dx. Now, and we know that a comma b equals ab minus ba, we know already. Okay. So now using that relation, we have minus x d psi by dx plus partial d by dx, that xy, x psi. Now keeping the first term as same, second term just take the second term. This is, we are going to differentiate x and psi with respect to x. So now we'll have to keep differentiation of uv method. So we'll have to keep u as constant, differentiate v, plus v as constant, differentiate u. So similarly, x, keep x as constant, differentiate u, that will give us, differentiate psi, that will give us d psi by dx, plus keep psi as constant, differentiate x, so dx by dx. Now look at the first term and the second term, both are the same, so we can cancel out. And third term, dx by dx will get cancelled and we will have psi alone. So I get cross psi. So that will answer is I get cross psi. So this is by means of coordinate representation. Now we'll go for the same thing as momentum representation. And of course, as I said earlier, the momentum representation, which is the Fourier transform of x and p. Okay, x. The momentum representation and the operator x is given as plus psi h cross partial d by dp. So x comma p acts on psi will give us. Now instead of x operator, we are going to substitute I h cross d by dp comma p, and we will have to use ab equals ab minus ba, their formula. So just you pull I h cross out. So that's a mistake here. So we will have to pull I h cross out. That will give us, that will I h cross we have pulled out. So now we will have to differentiate. So d p psi divided by dp minus p d psi by dp. So first differentiate keeping p as constant. So p d psi by dp. Now differentiate dp keeping psi as constant. So psi dp by dp minus p d psi by dx. Okay, the first term and third term will get cancelled, and of course in the second term dp by dp both will get cancelled. So you have I h cross psi. Okay, so in both the ways we have proved that the commutation relation x comma p equals I h cross. Okay, now we'll go for problem number 3. Evaluate x comma p square. So x comma p square we are going to evaluate. So x comma p square can be written as in the expansion form x comma p, p plus p x comma p, and of course we know the answer for the commutation x comma p is nothing but I h cross. So substitute x comma p commutation I h cross, this is p, plus p operator is there. Instead of x comma p you can substitute again I h cross. So that will give us, now 2 I h cross as common we have taken out. Then we have p, instead of p you can substitute minus I h cross partial d by dx. And of course we know that I into I squared minus 1, so that will give us plus. So the answer will be 2h cross squared partial d by dx. The answer of the commutation x comma p squared equals 2h bar squared partial d by dx. Now we will go for the problem number 4. Determine the eigenvalues and eigenvectors of the matrix. So this is 2 by 2 matrix. In row wise it is given as 3 2 2 0. So we are going to take A as 3 2 2 0, the matrix, and the characteristic equation is given by A minus lambda I equals 0. Here I is nothing but your unit matrix 1 0 0 1, and A minus lambda I will give us 3 2 2 0 minus lambda 1 0 0 1. So that will give us row wise 3 minus lambda 2 2 minus lambda, which is equal to 0. Now we are going to factorize this one. So of course taking the determinant value, that will give us 3 minus lambda minus 4 equals 0. So multiply 3 minus lambda with minus lambda will give us minus 3 lambda plus lambda squared minus 4 equals 0. So we will get lambda squared minus 3 lambda minus 4. It's a quadratic equation. We can get the values of lambda. We are going to, after factorizing, so which is nothing but lambda minus 4 lambda plus 1, just factorize, which is equal to 0. So lambda equals 4 and minus 1. So these are the eigenvalues of the given matrix. Now we are going to find out the eigenvectors. So eigenvector is the solution of this matrix. First we are going to take lambda as 4. Of course we have got 2 values because this is 2 by 2 matrix. So we have obtained the 2 eigenvalues. First we will take lambda as 4. So when lambda equals 4, substitute in the Slater equation. So this is nothing but a Slater determinant equation. 3 minus lambda, 2 minus lambda equals 0 is the Slater determinant equation. Now we are going to get the eigenvectors. So 3 minus lambda, instead of lambda substitute 4. So 3 minus 4, 2, 2 minus 4, and matrix multiplication with x11, x12, which is equal to 0. So 3 minus 4 will give us minus 1. So minus 1 multiplied by x11 will give us minus x11. And of course 2 multiplied by x12 will give us 2x2. So you add these two, that will give us 0. Now the normalization condition is given by, of course we know that x11 square plus x12 square equal to 1. Okay. So now normalization condition, and we know that n equals 1 divided by root of a square plus b square. So will give us the normalization constant will be n equals 1 divided by, and the coefficient of this one will be 1 and the coefficient of this one will be 2. So this will give us, of course, minus 1 whole square. The coefficient of x11 is minus 1. So minus 1 whole square will give us 1. So 1 square plus 2 square, that will give us 1 divided by root of 1 plus 4, which is equal to 1 divided by root pi. So this is the normalization constant. So x11, x12 column wise, this is the eigenvectors which are given as 1 divided by root of root pi minus 2 divided by root pi. Okay. Similarly, we will take lambda equals minus 1. Of course, we have obtained lambda equals 4 and lambda equals minus 1. So two eigenvalues, correct? Lambda equals 4 and lambda equals minus 1. You just take lambda equals minus 1 and substitute in the slatted determinant matrix, which is nothing but is given as 3 minus lambda, 2, 2 minus lambda. So which is given as 3 plus 1, 2, 2, 2 plus 1, x21 this time, x22, which is equal to 0. So 3 plus 1 give us 4, and here you can get 2. So that will give us 4 x21 plus 2 x22 equals 0. We can write this as 2 x21 plus x22 equal to 0, dividing by 2. That will equate that equation. So of course the normalization condition is given as x21 square plus x22 square, which is equal to 1. So n equals 1 divided by root of the coefficient of the first one. X21 is nothing but 2, so 2 square. The coefficient of second one, x22, is nothing but 1, so will give us 1 square. So which will, the answer is 1 divided by root of 4 plus 1, which is equal to 1 divided by root pi. Okay, we already used n equals 1 by root of a square plus b square, which is as a normalization constant to find out. Now the eigenvectors are given by x21 and x22 are given as 2 divided by root pi, 1 divided by root pi. So this is what we expect. We'll go for problem number 5. Show that any two eigenvectors corresponding to two distinct eigenvalues of a Hermitian matrix are orthogonal. I repeat, show that any two eigenvectors, so we are going to have two eigenvectors corresponding to two distinct eigenvalues. Okay, so we have separate eigenvalues of a Hermitian matrix are orthogonal. So we are going to find out lambda, that is lambda and lambda 2 are eigenvalues. So they are two distinct eigenvalues, and we are going to find out and when they are not equal and the wave functions are orthogonal to each other. Okay, so that's our idea. That is psi1 and psi2 are two eigenvectors. Okay, two separate eigenfunctions, and we are going to find out if the eigenvalues are different, these two eigenfunctions must be equal to 0. Okay, because they are orthogonal to each other. So this is what we are going to prove. Now psi1 and psi2, just take two eigenfunctions, two eigenvectors. Lambda and lambda 2 are corresponding to eigenvalues. Okay, now eigenvalue equation are given by a psi1 of x equal to lambda 1 psi1, a psi2 equals lambda 2 psi2. So we will keep this as equation 1 and 2, and of course given that lambda 1 is not equal to lambda 2, it's given that. Now you just multiply equation 1 by psi2 star. So equation 1 is given as extreme right, a psi1 equals lambda 1 psi1. Okay, so now multiply this equation by psi2 star, the complex conjugate of psi2 star. Now psi2 star a psi1, which is equal to lambda 1 psi2 star psi1. Now you just pre-multiply equation 2. This is equation 2. with psi 1 star. So A psi 2 multiplied by pre-multiplying by psi 1 star. So that will give us psi 1 star A psi 2, which is equal to lambda 2 psi 1 star psi 2. So this is equation 4. Now take the complex conjugate of equation 3. Just take the complex conjugate of equation 3. On both sides you are going to have complex conjugate. So psi 2 star will become psi 2. Your A will become A star. Psi 1 will become psi 1 star, which is equal to lambda 1 will become lambda 1 star, and psi 2 star becomes psi 2, and psi 1 becomes psi 1 star. You compare equation 4 and 5. Compare equation 4 and 5. You just compare. Left hand sides are equal. See, left hand side psi 2 of x, here also we have psi 2 of x. Psi 1 star of x, here also we have psi star of x, except A and A star. Suppose if the condition is A equals A star, then left hand sides are equal. If left hand sides are equal, right hand side must be equal. So equating the right hand side, we have lambda 1 psi 2 psi 1 star, which is equal to lambda 2 psi 1 psi 2. Suppose if we have lambda 1 star equals lambda 1, then we can write this equation as lambda 1 minus lambda. You just bring right hand side terms to left hand side and making the common out. So lambda 1 minus lambda 2 psi 2 psi 1 star, which is equal to 0. Now we can say that lambda 1 minus lambda 2 equals 0, or psi 2 psi 1 star equal to 0. Lambda 1, it's given as lambda 1 minus lambda 2 because they are not equal. It's given as lambda 1 is not equal to lambda 2. So only possibility is the wave function should be equal to 0. That is psi 1 star multiplied by psi 2 of x, which is equal to 0. It implies that these two eigenvectors are perpendicular to each other. They are orthogonal to each other. Okay, so this is what the problem is. Now we'll go for problem number 6. Determine whether the following set of vectors is independent or not. So now 3 vectors are given and we are going to find out whether they are independent or not. For any linearly independent vectors, we know the equation C1 U1 plus C1 U2 plus C1 U3 equals 0. So we know already. That is C1 U1 plus C2 U2 plus C3 U3 equals 0. So that's a mistake here. So it must be C1 U1 plus C2 U2 plus C3 U3, which is equal to 0. Now compare the coefficients. So 3 equations are given. U1 equals 2y minus j plus 3k. U2 equals j minus 2k. And U3 equals 2y plus j. So just we are going to equate the coefficients. Now first equation, just take the first equation. So this is nothing but your 2c1. Okay, 2c1. That is the coefficient of I is nothing but 2. So we have written as 2c1. Okay, and the coefficient of I is here, it is 0. So plus 0. The coefficient of I here, it is 2 for U3. So this must be 2c3. So 2c1 plus 2c3 equal to 0. So we have compared the coefficient of I here in the first equation. Now compare the coefficient of j in all the 3 equations. That will give us minus c1. Here it is plus c2, and of course this will be plus c3. Okay, because j coefficient of j will be 1, so this must be c3. Now compare the coefficient of k here. So this must be 3c1. Here it is minus 2c2. Here it is 0. So which is equal to 0. Now take the first one, first equation. 2c1 plus 2c3 equals 0. It implies that 2c1 equals minus 2c3. So c1 equals minus c3. 2 will cancel. Okay. Now take the third equation, and this will give us c2 equals 3 by 2 c1. And of course we have already obtained c1 equal to minus c3. So, and c2 equals 3 by 2 c1. You substitute in the second equation. So that will give us minus c1 plus instead of c2 substitute 3 by 2 c1 plus c3 is a substitute minus c1. Okay. So c3 will be your minus c1. So will give us now this c1 and this c1 will cancel. We have 3 by 2 c1, which is equal to 0. It implies that c1 equals 0. If c1 equals 0, and C3 must be equal to 0. If C3 equals 0, so C2 must be equal to 0. So C1 equals 0, C2 equals 0, C3 equals 0. It means that they are all linearly independent vectors. Okay. Oh, that's a mistake here. C1 equals minus C3. So instead of C1, C3 we can substitute minus C1. So here there must be minus C1. Here there must be minus C1. Okay. So C1 equals minus C3. You substitute in the second equation will give us minus C1. So again we'll get the common term out. Again we will get minus C1. Here we go plus 3 by 2 C1. Again we'll have minus C1. Again you pull the terms, common terms out. However, we will get the C1 equals 0. Okay. So the set of vectors is linearly independent. Now we will go for the problem number 7. Let the matrices A is given as 1 0 0 row wise 0 7 minus 3i 0 3i 5, and B matrix is given as 0 minus I 3i minus I 0 I 3i I 0. Are they Hermitian matrices? First we are going to find out whether these matrices are Hermitian or not. Then second one is determine the eigenvalues of A and B. So we are going to find out the eigenvalues of A matrix and B matrix. And we are going to calculate the trace of A and determinant of A. And we are going to verify trace of A is the addition of eigenvalues. Of course, that's a formula for trace of A, which is the addition of diagonal elements, which is the addition of eigenvalues. And determinant A is nothing but the multiplication of eigenvalues. So we are going to find out the eigenvalues. We are going to add the eigenvalues. That will give us the answer as trace of. We are going to multiply the eigenvalues. That will give us the answer as determinant of A. Okay. So first we will find out the first subdivision, which is nothing but are they Hermitian matrices. So A in row wise is given as 1 0 0 0 7 minus 3i 0 3i 5. Your A dagger is a Hermitian matrix. And what is the procedure for taking Hermitian matrix? Just to change the rows in columns and take the complex conjugate. So first we will change the rows. So 1 0 0 is given as 1 0 0 column wise. 0 7 minus 3i will give us 0 7 plus 3i. So we have to take the complex conjugate. Similarly, the last row is 0 3i 5 will get us 0 minus 3i 5. You compare A and A dagger, both are equal. So we can say that A is the Hermitian matrix. Okay, now we'll go for B. B matrix is given as 0 minus I 3i minus I 0 I 3i I 0. Just take B dagger. As I said earlier, that is we are going to take the rows as column as rows, and we are going to take the complex conjugate. So it will get as 0 I minus 3i I 0 minus I minus 3i minus I 0. You compare B and B dagger. B and B when you are going to compare is exactly equivalent to B equals minus B dagger. So this is not a Hermitian, but it is anti-Hermitian matrix. So B is an anti-Hermitian matrix and A is a Hermitian matrix. For all Hermitian matrix we will get a real eigenvalue. For all anti-Hermitian matrix we will get complex eigenvalue. Okay, so whether we are able to get the same thing or not, we will check. Now we will go for the second one, which is nothing but eigenvalues of A. Just take the eigenvalue. Okay, and we are going to take the matrix as A equals 1 0 0 0 7 minus 3i 0 3i 5. Take the secular equation. Cartesian equation is given as A minus lambda equal to 0. So A minus lambda equals 1 0 0 0 7 minus 3i 0 3i 5 minus lambda and unit vector, which is given as this equation 1 minus lambda 0 0 0 7 minus lambda minus 3i 0 3i 5 minus lambda, which is equal to 0. Now just take the determinant. So when you are going to take the determinant, that will we will get as 1 minus lambda multiplied by 7 minus lambda 5 minus lambda plus 9i squared. Okay, so now just take 7 multiplied by 5, that will give us 35, minus 5 multiplied by minus lambda multiplied by 5 will give us minus 5 lambda, and similarly 7 multiplied by minus lambda will get minus lambda 7 lambda, and of course minus into minus plus, so plus lambda squared. I squared is minus 1, so we will get minus 9, which is equal to 0. So simplifying, we will get 35 minus 9 will give us 26. Lambda squared is here. Here we have minus 12 lambda. So 1 minus lambda, lambda squared minus 12 lambda minus 26 equal to 0. We are going to factorize the quadratic equation using the formula minus b plus or minus root of b squared minus 4ac by 2a. So of course, if it is equal to 0, we will get lambda equals 1. And this is equal to 0, we will get lambda squared. So of course, use this formula, we will get the factors of lambda, which is given as 12 plus or minus root of b squared minus 4 multiplied by 1 multiplied by 26 divided by 2. So 12 plus or minus root of 144 minus 104 by 2, 12 plus or minus 2 root 10 by 2. You pull 2 out in the numerator, just pull 2 out common as common. So 2, 6 plus or minus root 10, 2 will cancel, we have 6 plus or minus root 10. So we have 3 factors as lambda equals 1, lambda equals 6 plus root 10, and lambda equals 6 minus root 10. So they are the eigenvalues of A, and of course all the eigenvalues, just look into, they are all real eigenvalues because A is a Hermitian matrix. Okay. Similarly, we can go for eigenvalues of B. Just check it out, and you will get as lambda 3 factors. You will get as lambda equals 3i, and lambda equals minus I plus root 17 by 2, and lambda equals plus I minus 3 plus root 17 by 2. So you just look at all the 3 factors of lambda. So they are all complex conjugates, see, not complex numbers. So they are all complex numbers because B is an anti-Hermitian matrix. Okay. So it brings out the fact that eigenvalues of A seem to be real whereas B are imaginary. So because A is a Hermitian matrix and B as anti-Hermitian matrix. Now calculate the third part. Calculate the trace of a matrix. Trace of a matrix, already we know that addition of diagonal elements. So which is nothing but 1 plus 7 plus 5. So trace of a matrix is given as 13. Okay. Now just take the eigenvalues of A matrix, which is nothing but 1, 6 plus root 10, 6 minus root 10. You add all the 3. So that will give us root 10 minus root 10 will get cancelled. 1 plus 6 will give us 13. Trace of a matrix also 13. So it is verified that trace of a matrix is nothing but the addition of eigenvalues. Now we will go for determinant of A. Determinant of A is given as 1 multiplied by 7 multiplied by 5. So 7 multiplied by 5 minus 3i multiplied by minus 3i will give us 35 minus 9, which is equal to 26. What are the multiplication of eigenvalues? Which is given as 1 multiplied by 6 plus root 10, this is another eigenvalue. 6 multiplied by root 10 is another eigenvalue. So we will give us 36 plus 6 root 10 minus 6 root 10 minus 10. So the second term and third term will cancel because opposite side. So we will have 36 minus 10, that will give us 26. So it is clearly it's proven that determinant of A is nothing but the multiplication of eigenvalues. Okay. So that's all for today's session, students. We will go for the next class. In the next class, we will see in the next class.